I bought a hardness tester. I saw this at a swap meet and it just had to come home with me. Now, I had no idea how these things worked. I had no idea if this one worked at all, and I had no idea if it was missing any important pieces. Spoiler alert, it was, but it's nothing we can't deal with. Welcome back to Cloud 42. I'm James. Well, a couple of weeks ago, I had the opportunity to attend the Bar Z Summer Bash. And some of you know this because you were there too. It's always such a great opportunity to actually meet some of the people who watch the channel. I'm just here in my shop talking to a camera, and it kind of really makes it real when I meet some of the people that actually watch and enjoy seeing what I do here. Now, one of the big attractions at the Bar Z Summer Bash every year is the swap meet. There's always all kinds of great stuff. Tom Lipton always loads up a truck full of stuff and brings it down, as do a bunch of other people. And this year at the swap meet, this was sitting on one of the tables. Now, this is a Mitutoyo Rockwell hardness tester. And this is the model 940-131. I really have no idea how old it is. Its condition belies its age. I did reach out to Mitutoyo to try to see if I could find manuals for it. They found manuals for a similar model, but they said this thing is more than 40 years old, so it's just not something that they have. I will take the manuals that I have and the other similar manuals that I've managed to find and put those someplace. There'll be some links down in the video description. Now, I have always wanted a hardness tester. I have a set of hardness testing files, but that is not the same as an actual Rockwell hardness testing machine, which is what this is. Now, this is not a Rockwell C hardness tester. This is what's called a superficial hardness tester, but we'll get more into that in a minute. Now, I didn't know anything about that. I didn't know what that meant. I mean, it says superficial right on the front, but I had no idea what that meant. I had no idea how these things worked. I really didn't know how this worked. We tried to test it at the bash and it just was not behaving properly, but I didn't know enough about them to understand whether that was a big problem or a small problem, but the price was right, so I brought it home. And it turns out that the problems that I was encountering with it were minor and easily fixed, and the parts that were missing are easily replaced. Now, if you've ever watched a video about one of these hardness testers, you know that there is some kind of a hardened point and an anvil, and you put your part in there and then raise it up into the point. There's a dial indicator, and you're supposed to run it several turns in one direction, and then you flip a lever and it goes back the other direction. And then you flip the lever again and it goes back again, and then you read a number, and I never understood what any of this was for. It was just a bunch of rote memorization. Do this, do this, do this, read the number, and I never understood how any of it worked. So let's start with how any of this works. So what exactly is hardness and how do we measure it? Well, hardness is defined as a material's ability to resist plastic deformation. Now, plastic deformation is the kind that's permanent. Elastic deformation is the kind that bounces back when you remove the load. Now, this is different from strength. Strength is a material's ability to withstand a load without failing, but hardness is specifically about deforming that material. And we test it by taking some kind of a point and forcing it into the surface of the material under a calibrated load. Now, there are about 15 different Rockwell scales for hardness, and they all involve using different shapes and sizes of points pressed into the material with different loads, and then you have a different formula for calculating a hardness from the depth that the penetrator goes into the material. The most common one you're going to see in a machine shop is going to be Rockwell C, or HRC. And the reason is because this particular scale is useful for most heat-treated steels. You may see HRB or Rockwell B for softer, like annealed materials, but for heat-treated stuff, you're usually going to see HRC. And HRC uses what's called a spheroconical indenter. It's a 120-degree cone indenter with a diamond point with a 0.2 millimeter nose radius. And this is pressed into the material with a specified force, and you just measure how deep it goes to determine the plastic deformation. But as always, it's a little bit more complicated than that. There are two loads that are used for testing. There's L0, which is the initial load, and in the case of Rockwell C, that is 10 kilograms force. And so when you load up your part in the machine and put the point on it and you initially preload it, you're going to load it up to 10 kilograms, and that's going to force the tip partway into the material. And at this point, you then zero your dial. That is the starting point for the test. Now, the reason you have that initial force is because if you just set it on the part, you don't really know if you're in intimate contact there. You don't know how hard the part is pressed down on the anvil. And so actually having some initial force on it and getting a small initial indentation gives you a repeatable starting point for the test. And then to actually perform the test, you apply L1, or the major load or the testing load, to force this further down into the part. And in the case of Rockwell C, this is 150 kilograms force, and then that gives you some new position where the indenter has now made its way further down into the material. But this is not the point at which you do the measurement. And the reason for that is because some of this deformation is plastic, which you want to measure, but some of it is elastic. It's going to bounce back when you remove the load. And the other problem is that you have flex in the machine. So you've applied 150 kilograms of force. That's actually going to expand the throat of the tester a little bit, because the frame, even though it's very heavy and very strong, is going to flex. So to finish the test procedure, you remove load 1 and go back to just the 10 kilograms of force. The point will come up a little bit, and then this gives you the point at which you measure. And the difference between the 0 point where we started and the point where it comes to rest with exactly the same load after indenting is called D. And so then to actually measure the hardness, HRC, this is 100 minus D times 500. So D is measured in millimeters. You just multiply that by 500, subtract that from 100, and that gives you your Rockwell C hardness score. And for every different Rockwell scale, there's a different size and shape of indenter. Some of them use steel balls, some of them use this spherical diamond, and then there are different loads that are applied for the different tests. Now, the particular machine that I have does not measure Rockwell C. It measures what's called superficial hardness. So instead of penetrating deeply into the material to measure the hardness of the interior, it uses a light load and only penetrates partway into the surface. This is called a superficial test, and there are 3 different scales on this machine: 15N, 30N, and 45N. And the one that I prefer to use is 45N, and that's how I have the machine set up. And L0, the initial load, is only 3 kilograms, and the testing load is 45 kilograms. And then because this doesn't penetrate in as far, the formula is a little bit different. The 45 in hardness is 100 minus D times 1,000. Again, because it's not going in as far, you have to multiply by a larger number to get a useful range of hardness values. Now, it is possible to convert between these different scales. In my case, I usually want to know Rockwell C, but the tester I happen to buy only has the scale for the superficial. It has the times 1,000 dial indicator on it and the 3 kilogram initial load, and I can't change those things, so I need to convert. This is not a linear relationship, but it is convertible, and there are charts available. There are some caveats. The 45N, this is a superficial hardness, so it's only measuring near the surface of the part. So if you have a case hardened part, this is going to usually measure the hardness of the case, not the interior. If your part is through hardened, then it doesn't matter, because the hardness of the surface is the same as the hardness of the interior. The other thing that's really different about these is that the superficial scales can be used to measure thinner parts. If you have a thin piece of sheet and that's sitting on top of the anvil, and you try a deeply penetrating test like Rockwell C, you're really going to be measuring the influence of the hardness of the anvil underneath and not just the material, where with a superficial scale, since it's only measuring near the surface, you can measure thinner materials. At the business end of the machine here, we have the penetrator or the indenter. Now, this is a braille indenter. This is the spherical diamond, 120 degrees with a slightly rounded tip. and that just fits into the spindle of the machine here. Now there is a little screw here, but it's not really a screw. It's just a spring-loaded plunger. You can unscrew it, you're not supposed to. The tips just slide in and out with friction and are held by that little spring-loaded pin. Now this whole spindle of the machine is spring-loaded and it's connected to the dial indicator. So I'm just pushing up here and you can see that that is turning the dial. The minor load is applied to this using a spring, and that spring is located in here. There is some adjustment that you can do underneath here with a face spanner, at least it looks like that. There's 4 locking set screws and some pinholes. I have not touched it at all, and I do not want to touch it. This is the one part of the machine that kind of scares me, because if I open that up, I'm sure things are going to fly out. But it is working, so fortunately I do not need to touch that. Now, because this is a superficial tester, there is a 3 kilogram spring in there. If this were a Rockwell C tester, it would have a 10 kilogram spring. Then down below the point, we have the anvil, and that anvil is sitting on a large screw. And you can turn that screw with a capstan. You're actually turning the nut on the screw to raise and lower the anvil. And so the purpose of this is to be able to put your part to be tested on here. This is a smooth, flat ground surface, and you would want your part to be smooth and flat so that it bears evenly on that, and you can raise that up into the point on the machine and compress the spring in the point to apply the appropriate preload before you start the testing. Now, this screw has a dust cover on it, and you can run it down quite a bit to increase the size of the throat of the machine. And the screw actually will go out the bottom and hit the desk, and so in the manual they tell you that you should put a hole in the workbench underneath the machine so that you can lower this as far as possible. Now, on the back of the machine there is a stack of weights here hanging on a lever, and this lever, if I lift it, you can see it moving here. It goes all the way up to the test point on the machine, and these weights through this lever apply the major test force downward on the point. And then there's another lever here on the side that actuates through this lever to lift that weight off when it's not needed. So when I turn that lever, you can see it goes up, it lifts these weights, and now that takes the weight off of the point, and when I release this lever, it goes back down slowly and reapplies the weight here through the lever to the testing point. Now you can change the major load on the machine by changing how many weights are stacked on here. And in more modern machines, there will be a big knob on the side here because all of the weights are actually inside the column of the machine. And you're doing essentially the same thing. You're just putting weights on and off of the lever, but you're doing it with a cam that just lifts individual weights off of the mechanism. But on an old school machine like this, it's all just out in the open, easy to see, easy to maintain. This thing is just dead simple. And then the last functional component of the machine is over here on the left, and this is an oil-filled dash pot. And that is just attached between the frame and the lift lever, and the whole point of this is just to slow down the descent of the weights when we're applying the weight to the point. So when I flip the lever to drop the weight, you can see this falls slowly, and that is just oil resistance in this dash pot. And that is adjustable. There's a little needle valve up here. There is a spec for the oil that goes in here, and it's supposed to be a mix of a couple of different motor oils. It's actually really simple, and it's really not that critical because you can adjust the needle valve here, and the manual just calls for this to be adjusted so that it takes 5 to 8 seconds for it to fall. And the only reason that's there at all is just to keep this point from slamming down onto the workpiece so that you don't chip the diamond. It doesn't affect the accuracy of the measurements at all. It's just there to keep you from breaking the diamond. When I bought the machine, these were the weights that were hanging on the back of it. There's the initial hanger with a weight on the bottom. It's labeled 15 kilograms. And then this weight was sitting on top of it, also labeled 15 kilograms. But curiously, it also says 15 plus 15 plus 15, 45 kilograms. And it took me a little while to figure out what that meant. And that is not actually the weight of these. These are quite a bit lighter than they're marked. But this is not the weight of the mass of the weight. This is the actual weight that gets forced down on the point when this weight is hanging on the end of the lever arm. So when you hang this on the back, you get 15 kilograms. If you put a second one on, you get 30 kilograms. Now, I want to do 45, so I need another weight, which did not come with the machine. We'll get to that in a minute. Now, the way these are actually constructed is these are just turned out of aluminum. This is, again, just turned aluminum with some paint on it, and then there's a little plate on the top attached with a couple of screws. And then if you pull that plate off, you can see there are lead chips inside. So this is just turned to be slightly under the desired weight, and then the center of this thing is loaded up with these lead chips to calibrate it to the exact weight desired. So what is the actual weight of these things? Well, this one that goes on initially is 357.3 grams, and this one is heavier, 592.7 grams. So why is this heavier than this? Well, I'm pretty sure they're both marked 15 kilograms. They will both result in 15 kilograms of force down on the point when you apply these to the end of the lever arm, but this one goes on initially, and so it doesn't account for the weight of the lever. The lever itself has some mass. When you hang this on it initially, that results in 15 kilograms down on the point during the test. If you add another one of these, you get 30 kilograms on the point, and if you add a third one, you'll have 45 kilograms on the point. Now, I could do a 15N test with just this weight. I could do a 30N scale test with this weight added, but I want the third weight that did not come with the machine so I can do 45N testing. So I made one. This is actually 3D printed. I printed this out of silver silk PLA, and I tried a couple of different filaments just trying to find something that kind of matched the look of the aluminum. You'll also notice that the top is a little bit different shape. I just patterned that after this and the bottom after this so that these will then stack together into a weight stack just like I presume the originals did. I do have at least one photo that shows all the weights, so I'm pretty sure this is how it was supposed to work. And I just printed this on the Bamboo Lab H2D so I could do a bunch of multi-material stuff. I could use support material for these hollows. I've got the silk PLA, I've got black PLA, I've got a cyan PLA and white PLA to do the markings, just to make it look as similar to the original as I possibly could. Now, of course, the PLA is not nearly heavy enough, and you can probably hear this. I just loaded this with lead shot. So top just screws off. We've just got some coarse screw threads, and it's loaded with lead shot that I bought from Amazon. And the reviews for this lead shot say it's terrible because the pellets are all deformed so they don't fly straight, but that does not matter for this application. It's exactly what I needed. Now, I did several versions of this, and I had just a cap on the top with a seam in it, and I just could not hide the seam. So I redesigned this with an overlapping lip. So it screws all the way down so the seam is against this other color of plastic and you cannot see it at all. And on the machine, if you weren't looking, it's pretty close. It's not exactly the same luster as the aluminum, but it's not bad. Now, I wasn't sure, but I guessed that this was supposed to be the same weight as this, and I'm getting accurate results from the testers, so I assume that was correct. So the original was 592.7 grams, and the new one is 592.7, because I have a scale and that's how much lead I put in it. So let's put this all into practice and actually test a specimen. I have a sample here. This I bought off of Amazon. This is calibrated 62.1 HRC. So we know what the hardness of this is, and we can use it to check our tester. Now, the test procedure is we need to apply first the minor load of 3 kilograms. And we do that by just turning the capstan here and raising the screw and compressing the spring. How much do we compress the spring? Well, this machine is designed so that you go 3 revolutions on the big dial. There's a small hand down here with a red dot to let you know when you've got those 3 revolutions. And when you do that, you end up with 3 kilos on the test point. So we'll do that, go up here, go around 1, 2, 3. Now the only thing, there's nothing magic about 3 revolutions, except that's just how much the spring in this machine is designed to be compressed to get the 3 kilos. So then we need to apply the major force, and we do that by just releasing this lever, which drops the weights on the back, and now that's going to apply 45 kilos to this point. So now we've got 45 kilograms of force pressing down, and we can see that the dial has fallen from 100. That's our 100 minus 1,000 times the movement here in millimeters. But of course we can't use this value because the machine has also flexed when we applied that 45 kilos of force. So we have to lift that back off and the needle comes back up. And where we end up is at about 69. Nice. So we started with 100, we've subtracted 1,000 times D, the depth of the penetration, and we're now sitting at 69. Now that's 69 on the 45N superficial scale. I would actually like to know the Rockwell C hardness of this part, because that's what I care about, and if I had found a Rockwell C tester at a swap meet, I would have bought it. But I have a conversion chart that I put together here from sources available on the internet, and we'll just come down here and find 69 45N, and that is equivalent to 62.1 HRC. And lo and behold, 62.1 is exactly what is laser marked on the side of my test standard. So that's good. Now I actually have a digital force gauge, so we might as well measure and see if we're getting the forces we expect out of the spindle. Now this is just a really cheap import gauge. I don't really trust the values that much. The fact that we're getting good results out of the tester tells me things are working okay, but let's just see what we get. So we'll go ahead and load this up, and we'll bring this up 1, 2, 3 turns on the dial, and you can see we've got about 3 kilos of force on the meter. It's bouncing around 3.03, 3.05. Zero this, and then we'll drop the major load, which should be 45 kilos. And it looks like we've got about 41.67. Again, I don't trust the meter, but we're at least in the ballpark. And then pull the load back off. And now we're back down to our 2.89, 2.9, about 3 kilos. And we're sitting here right about 64. If I look at my chart, 64 is 57.9 Rockwell C, and this is hardened and tempered A2 tool steel, so that sounds like we are in the ballpark. So even though there's extra flex here in the transducer, it doesn't really affect the measurement because we are initially loading it to 3 kilos, adding the test load, then pulling it back, so whatever flex is in here in 3 kilos gets canceled out in the reading, which is pretty neat. Well, now we have a hardness tester in the shop, and in fact I have already used it on a project that I filmed that has not gone live yet. Be sure to subscribe to the channel if you don't want to miss that. Now I would love to hear from you. Do you have any experience with these machines? Do you have the actual correct manual for this model? Do you know anything about converting these? Can these machines be converted from the superficial hardness to Rockwell C? I think you need a new dial to do that, but I'm actually not sure. If you've got any information about that, please throw that down in the comments. If you found this video useful, give it a thumbs up. Again, feel free to subscribe to the channel and maybe think about supporting the channel over on Patreon. Patrons get access to downloadable files for all of my projects, including that weight that I put on the back there. I'll have those files up and available if you want them. Thank you for watching.